Day 2 of section 4.3, still working with some Riemann sums and evaluating definite integrals from an area perspective. So I know you don't have this particular screen on your notes, but I just want to lead into our notes by looking at this problem here. I've got the graph on the right that represents the parabola negative x squared plus 5, and I want to know, is this a left-hand or right-hand Riemann sum based on the rectangles shown? Would you be able to figure that out? What I would do is I would just pick a rectangle, and I'm going to choose the center one right here. Where does it hit the curve? Where's that intersection point? Well, right there is what determined the height for this rectangle 3. And that is on the left side of the rectangle. So that would lead me to believe that this is a left-hand Riemann sum. And if you look, you'll notice all these rectangles, their height was based on the left-hand side. So that's a left Riemann sum. Second follow-up question, could you tell me if this is a lower or upper sum? Well, that's almost even easier, isn't it? I notice I've got all this overage, the overestimation going on there with those rectangles. So that must mean I have an upper sum going on. The left-hand method is overestimating the area of this, or the value of that integral. So this upper sum is associated with overestimation. Now, what type of function is this? Is it a increasing function or is it a decreasing function? Well, obviously my y values are falling as I head to the right, so this would be a decreasing function in this scenario. Decreasing functions that have left Riemann, left rectangular method going on would definitely give us overestimations. So now take that into this next problem, this problem 45 that was in the textbook. They ask us to do both lower and upper estimates of the integral from 0 to 10 of f of x. And here is the table that is representing a few key values from the function f. And they want us to use a rectangular method, once doing the lower estimate, once doing the upper. So I think what I'll do is I'll break this up into a few intervals. And there's interval 1, interval 2, interval 3, interval 4, interval 5. So I'm going to have 5 rectangles when I approximate the sum from 0 to 10 on this. Obviously here you can tell my delta x is 2 in every case, isn't it? I could go 10 minus 2 and I subdivided it 5 different ways, and it's 2, and it stays nice and consistent because we're counting by 2's. So delta x is 2 in this scenario. Let's do the lower estimate first. Now, do I want to use the left-hand approximation or the right-hand approximation for this? That is actually going to be determined on whether this is an increasing function or a decreasing function. And I notice I go from a y value of 32 to 24 to 12 to negative 4 to negative 20. Obviously, these y values are decreasing, aren't they? So my lower estimate for this decreasing function means that I would use, for a lower estimate, if it's decreasing, the left side will be larger than the right side. So I should probably use a right-hand method for my rectangular approximation, because the right will have smaller values because it's decreasing towards the right. All right, so we got that figured out. Let's go for an area approximation here. Well, delta x stays the same on every interval, so we could pull our delta x out front and say we've got 2 times each height of the rectangles, right? So in other words, I'm going to go 2 times. Now, since I want to use right hand, I'm going to eliminate working with the 32, and my height will be the 24 plus the 12 plus the -4 plus the -20 plus the -36. Those would all be the right-hand side. If I'm on the interval from 0 to 2, right-hand value would be 24. In my next rectangle, you can see how the right hand would be 12. My next rectangle, the right hand is 4, or -4 and -20. And then right hand means I'm going to use that last value. So there are those four, and I know you can probably do the math on that. It looks like I get -24 when I add those up. So overall, I'm getting a -48 for the value of the integral from 0 to 10. Now let's go and do the upper sum. And that's going to be based on a left-hand rectangular method. So left-hand rectangular approximation will give us the upper sum. And I got to clean up my box because I wrote all over this. Left-hand approximation, I need to take delta x times every height. My heights are going to be based on the left hand, so I won't be using the very last height. And that means I need to add together 32 plus 24 plus 12 minus 4 minus 20. And when I sum all that up, I end up with 2 times 22, and that gives me an approximation of 44. Did you notice what a big swing we had? First approximation was -48, and the next one is 44. That's a lot of difference, isn't it? It shows you, how accurate, inaccurate these approximations can be. We had, really two very different numbers on the left-hand versus right-hand approximations coming in. If you wanted to, you could graph this function out. Not entirely necessary. Number 50. Think about this. A function f is defined below. Use geometric formulas to find the value of the integral 0 to 8 of f of x. So I think I would probably take the time to quickly sketch this out. It looks to me like we got a piecewise function over here. So when x is less than 4, the value is 4. And we're running from 0 to 8. That's kind of key to pick up. So let's give ourselves a few spots on the x-axis. So I just counted by 2's. From 0 to 4, our f of x value, f of x is equal to 4. Well, that's a horizontal line. That really means what? Y is equal to 4. So 1, 2, 3, 4. And go ahead and take this on up to 8. That's where we're going to have to max out at. This first function, up to the value of 4, we have just a horizontal line, height of 4. For the next portion of our piecewise, it says f of x is equal to x. Well, we all know that this is a linear function, right? And that means that y is equal to x, up 1 over 1. If I start this at 4, and I plug in 4, it would say y equals 4. So we're picking up right where we left off. How about when we are at x equals 8? When x equals 8, y equals 8. So we get this linear function that's going to connect between 4, 4 and 8, 8. So the integral is going to be represented by the area that falls within that space. That's not too bad to calculate, is it? I could, now just visually, how do you want to calculate this area? Let's say, just to get some things down, the integral from 0 to 8 of f of x dx is going to be approximately, actually it's going to be almost exactly, isn't it? I'm going to chop across here and look at this as a rectangle that has dimensions equal to 4 by 8. That's going to give me 32 for an area there. So I had 4 times 8 plus then I've had that triangle up above it, and that triangle picks up an area of 1/2. Base would be 4, height would be 4, area 16, half of 16 is 8. So over here in my work, I'm going to show 1/2 of 4 by 4. And that means we are going to get approximately, or exactly, 32 plus 8. Our estimation of this integral is 40. Almost 80. Next one, 51 and 52. 51, it says the interval from 1 to 5, closed interval, is partitioned into n subintervals of equal width delta x. And x sub I is the left endpoint of the ith interval. So if I look at this summation here, they're really talking about a y value here, right? F of x sub I would give me some y value times some width of x, delta x. Essentially, I've got height times width. These are our Riemann sums, right? And that's going to give us area from 1 to n. We want to compare this calculation on the left to the calculation of the actual integral 1 to 5. Now this is going to be the exact area under the curve. And that what they're asking is a comparison, which is bigger, which is less than. So summation, if I base this on the left endpoint, and I'm starting at 1, because I noticed the index says from 1 to 5, left endpoint, well, that would create rectangles that are based on the left-hand side. And since this is a decreasing function, we're going to have some overage, right? I would say this left endpoint leads us to an overestimation of the area because we have a decreasing function. That means values on the left side are bigger than the values on the right side as it decreases. 52, I think we flip-flop around. We still got the same function. Now they're asking about right endpoints. Now my rectangle is based on the right-hand side of the curve. So following those intersection points of the curve, obviously we are in an underestimating because we have a decreasing function, so my approximation will be less than the actual integral value. Here I should have put a greater than, right? It was an overestimation. And finally, the last 3 problems to look at, intervals of integration. I want to talk about translations of the function and how does it affect area or the integral value. So you can use a graphing calculator to help you calculate these out. And go ahead and pop open your graphing calculator. Okay, I hope you have your graphing calculator, and we're going to look at how to do numerical integrations on our graphing calculator. First off, let's take our function square root of x plus 2 and plot this out. So let's just take a few key points. If I put in 0 into my function, I get out 2. If I put in 1, the square root of 1 is 1, I get out 3. And if I put in 4, the square root of 4 is 2. 2 plus 2 gives me 4. And that is kind of the end of the nicest values. I think if I put in 6, I would turn out with 4.4. So if you want that as a target point to finish this, there is our function. Now, rewriting this function, we were going from 0 to 6 of the f of x, which is square root of x plus 2 dx. And what we want to know is, what is the value of this? Well, our graphing calculators do a very fine job of doing this. You can access it through either the math menu, and option number 9 pulls in an integral for me, and I just have to fill in the spaces. So 0 to 6, got to put my function in here, which was the square root of x, and then it was plus 2. And now I got to tell it what variable I'm working with, so with respect to x, so my differential at the end is dx. And if I hit enter, it will tell me the exact value for this integral. And the exact value is 21.798. Nice. What did that calculate? That calculated the area under the curve and above the x-axis. So what it did, you might want to shade this in, is it calculated this value in a very precise manner. Okay, the next one, I want to take our original function and add 3 to it. What would that look like? Well, that would give us an integral from 0 to 6 of the square root of x plus 2, there's our function, plus 3 dx. Essentially, what is happening to our function? It's lifting it by 3 compared to this original. So this shifts up by 3. We could simplify this function a little bit, couldn't we? We could take 2 plus 3 and turn it into 5 and simplify it. So now that is what we're looking for. And I want you to graph that out. This function, I'm just going to make a copy of this for myself. Let's clone that and let's bring that over. Here's what it looked like. We know we are adding 3, so a vertical shift. There's 1, 2, 3, vertically shifts up by 3. You could tell me the answer on the value of this integral without having to go to the calculator, because essentially it took, you know what, even better would be to pull all this together. Let's clone all of that. I think this will be visually a better example. There's that function. Let's shift it up by 3. So it was at 2 over here on the left, and now it's going to raise up to 5. There's the area, and this area comprised 21.798 square units. What did I pull in underneath it? Nothing more than a rectangle that has a height of 3 and a width of 6. I'm bringing in an area of 18, correct? So I know that I've got 21.798 plus 18. This will give me a total area of 39.798. And 39.798 should be our answer. Let's verify it using the calculator. So what I did is I really took my original function, I'm just going to copy and paste, and we shifted it up by 5, or by 3, so that value at the end goes to 5. I'm going to hit enter. And there's that number, 39.798. Nothing more than bringing in a rectangle 3 by 6 underneath it. Vertical shifts, pretty easy to deal with on integrals. This next one has a little bit of fancy stuff going on, doesn't it? Now, this is just slightly different. It's the x plus 3 that's getting shifted. Well, your working pre-calc tells you that this is going to shift left by 3. That's a little different than just shifting this up. But if I look at my integral, look at how this interval of the integral changed. The interval also shifted, but the interval shifted as well, didn't it? Shifted left also, because it's asking us to run from -3 to 3, so it wants me to take the area from -3 to 3, not 0 to 6 anymore. So if I take this original function that was sitting here, and I shift it to the left by 3, I'm really just picking this whole thing up, and it's hopping to the left 3 units. Did the area change at all? No, it did not. It's still like the original, 21.798. This function would look like -3 to 3. F of x plus 3 would mean that my function really looks like x plus 3 plus the 2 on the outside. That's what that function changed into, didn't it? Now take your graphing calculator and let's just verify that the area did not indeed change. So I'm going to do a copy paste again. So let's copy that, throw it in, and I need to get underneath my radical sign, which now I am. Add on that 3, and let's see what the area comes up. Oh, no wonder why that's wrong, because I got the 5 still on there. And we did not vertically shift. So I'll get back to the 2. Sorry, guys. That's bad of me. And notice we also have to shift, because this integral is showing from, what, 0 to 6. Kind of good that I made these mistakes. Well, not really, but okay, so -3 to 3, update it, and now I promise you it's going to be 21.798. Oh, yay! 21.798. So you can see, though, just looking at this other one where we had it from 0 to 6, yeah, that area is different, isn't it? Because what it would have been doing was taking and doing an area out in that region, obviously more than what we picked up on the intended target. Excellent, you guys. I hope this helped just solidify a few concepts for you. See you tomorrow.